All right, so today's webinar is we're gonna concentrate on increasing accuracy and precision during dietary fiber analysis. We're gonna start with talk about background. We're gonna all get on the same page with a couple definitions and make sure we understand what that means. We're gonna talk about variables that impact precision, and this is generally during the conventional methods. We're gonna also talk about improving precision with automation. And then we're going to look at some actual data from the instrumentation. All right, for our discussion, so we're all on the same page, and Chris and I will throw a lot of terms around, but we want to make sure that we're all on the same page. So when we say classical or conventional method, we're referring to the method that has been run in the lab, generally on the benchtop for many years, maybe even decades. All right, they generally are volumetric or colorimetric, gravimetric. They have a high reliance on glassware, and they require a large amount of technician intervention, and that's generally where the imprecision comes into play. When we decide to automate a method, our goal is to keep the method chemistry. We're not changing the method at all. We are running the actual method as written. The only difference is we are automating it. So with any kind of an automated system, ease of service is very important. We have instruments all over the world, and back in the 90s, we didn't necessarily have support in every single country, so we wanted to make it accessible and easy for the end user to actually do the repair on the instrument if necessary. Now, we do have technicians, or we do have service personnel all over the world, but it's still nice to have a system that's very easy for the end user to repair. So we believe that simplicity is the result of profound thought. Right? And again, along with ease of service, we want ease of operation. We want really anyone to learn how to use the instrument within a run or two and have quality data. You don't have to spend a whole lot of time training folks.
Let me throw something in here, Nick, too, when it comes to the ease of service, specifically on dietary fiber. Over the years, as we've interacted with laboratories, we're actually in over 125 countries now. As we've interacted with laboratories, we've seen little things that we can do to make service simpler, make easy access, things like that. And a good example is with this dietary fiber instrument. When we designed this instrument, we decided to make it so the instrument could actually be, for lack of a better way of saying it, swiveled, so you don't have to disconnect anything. The whole unit actually tips into what we call the service mode, so all the moving parts, all the tubing, all those things are easily accessible by somebody standing in front of it. Which again, we just found in some laboratories, the bench space is such that it's a major thing. They have to disconnect an instrument and turn it around and all that. We've basically designed the dietary fiber instrument so it doesn't have to be moved to be fixed, which was just a real nice plus that we did. We were getting high marks because of that. Not only if our technical service people have to come in, which is rare, quite frankly, but just for general periodic maintenance that a end user might do, it's very simple for them to access it. It makes it very simple.
Okay. Along with with any automated system, the goal here is to reduce your technician intervention, which again we're going to talk about how that increases precision and accuracy. But another aspect is that it lowers per assay cost, and I believe this is your part, Chris.
Okay, so let's talk a little bit about the impact of the technician when it comes to variability. The methods that we do, and we'll hit on this near the end, but we can support AOAC 991.43, 985.29, and we even have extensions for what we call the codex definition methods, which are 2009.01 and 2011.25. We might actually add some additional ones in the future. But when you consider the method, let's just look at 99143 as kind of our example. There's a lot of issues when it comes to controlling temperature, controlling mixing, the transfer error, the filtration process, and things like that, which we'll be talking about. When we were designing the instrument, that was one of the biggest issues that we had to look at, and that's this idea of transfer. How do you do a digestion, multiple enzyme digestion, and then go from, if you will, the digestion phase and then transfer it into, in the case of the conventional method, a 60 milliliter fritted glass gooch in order to do the filtration, because there is that move from one to another. How do you reduce that? And so we're going to be talking about that. With the conventional method, that is an element of variation. How do they transfer it? Again, when you're talking about the amount of solution that has to be transferred into a smaller fritted glass crucible, that can have an impact on it. Temperature control is not critical across all samples. However, there have been some papers where they demonstrated that variations in the required temperatures, for instance, 60 degrees C for the amyl glucosidase or AMG, has had an impact if that temperature has been increased above the 60 degrees in some samples. So I would emphasize that temperature control, we did some Yoden studies early on, and we only found one sample in our studies where a temperature impacted a result. But again, in a literature review, I have found some other examples of temperature impact on specific sample types. And by the way, a lot of this is from a paper that I produced for the Dietary Fiber Conference in Istanbul, Turkey in 2016, and that paper certainly is available to you. Get a little bit more into details and specifics about these impacts on variability. But transfer error, temperature control are two elements. Again, transfer error more importantly than temperature control for most sample types. When it comes to agitation, the methods are not, in most cases, not real detailed on what the agitation level is. Agitation is necessary to provide surface area for the enzymes to do their work. So if the samples are not being thoroughly mixed through the solution, then enzyme access could be limited. In some of the methods, it specifically talks about using a shaker bath. For instance, in 991.43, it talks about continuous agitation in a shaker bath. It does not get too specific in the revolutions per minute, things like that. It just talks about continuous agitation. In 985.29, it talks about intermittent, or it specifically says in 5-minute intervals. If you go to the Codex methods, the 2009, 2011, it starts to get a little bit more specific on the types of agitation, revolutions per minute, and things like that. The key element really is this idea of access to the enzymes to the sample because of the surface area provided by agitation. If you think about it a little bit, if you put, and we actually did this study, if you take a beaker, which is generally what's used to do the digestion phase in the conventional method, and if you take that beaker and you put some solution in it, like let's just say water, and then while it's agitating, you drop into it a couple of drops of food coloring, you'll basically see that it does not disperse quickly. It takes time because that agitation is not very aggressive from the standpoint of moving the solution inside and whatever's in that solution, so it's got a lot of access. And so when we actually did a video of it, but it was hard to see in the video, but basically what happened is the color dye would kind of be a clump in the center of it, and over time it would start to disperse through the liquid, but it took a considerable amount of time for it to basically permeate the whole solution and change the color of the whole solution. And those are the kind of things we look at because we want to make sure agitation is enough to create a nice surface area, a nice flow of the sample within in this case, the buffer and the enzyme. So that's a critical issue and can have a significant impact on the results based on how the agitation is. When you look at the conventional method as well, there is an issue with filtration. Remember, the method, again talking about 991.43, the method talks about using a coarse 50 fritted glass crucible, 60 milliliter in size, and with a diatomaceous earth base that has been prepared in the beginning in order to improve or reduce, maybe is a better way to say it, the porosity of the gooch. A course 50 has a porosity of 40 to 60 millimeters, and so it's a fairly porous filtration. That's why the diatomaceous earth in the conventional method is so critical. When you do the filtration with the gooch crucible, remember you're taking a size of solution. For instance, in the upper digestion, when you're doing the enzyme digestion, you have about 50, maybe slightly more than that because of rinses, milliliters of solution that you're putting into the 60 milliliter crucible, which is fine. That's you'll have enough space. However, when you do the filtration of the precipitation phase, you're talking in excess of 350 milliliters that's being poured into a 60 milliliter fritted disc. And so there's this, basically you have to constantly be there to keep adding it on as it filters. Likewise, with the conventional method, using the fritted glass crucible with a diatomaceous earth base, it's not uncommon for the filter to clog. A gel forms in most of the samples that have been digested, and certainly after precipitation. And that gel needs to be broken, for lack of a better way of saying it. In 991.43, it basically talks about how you break the gel surface. In other words, you disrupt the gel, you don't disrupt the diatomaceous earth base. If you look at a laboratory doing it, you'll see there'll be a slight scratch, which would be expected in the diatomaceous earth base, but you do not want to dig into that, or specifically don't want to go to the glass in order to increase your filtration. If you do that, you're changing the porosity of it, and you're going to likely lose some of your particles in that process. So that's a critical issue. I would say probably one of the most impactful issues or elements of the conventional method, how they handle filtration. I always tell stories about some of the things I've witnessed in laboratories around the world, and one of the things that surprises me is how often people, because they get so frustrated with the length of time it's taking them to filter, they dig deeper and deeper into that diatomaceous earth in order to increase the filtration process. We even had a customer that I observed that they weren't just scratching the surface, they were, if you will, stabbing the fritted glass crucible all the way to the glass. You could actually hear them hitting with the metal spatula the fritted glass portion of the crucible, and they didn't see any problem with that. I was at another laboratory that showed me their method that they had videoed using a system that still uses crucibles with the diatomaceous earth. And the thing that amazed me is when they put the filtrate container on the fritted glass crucible, they actually picked it up off of the vacuum manifold and shook it. So they were dispersing the diatomaceous earth throughout all the solution. Boy, it filtered pretty quickly. That was pretty nice. But the bottom line was that's not what the method calls for, and most likely they were underreporting many of their results because of sample loss. And so, again, those are kind of things that happen because we can't necessarily control what the technicians are doing because they're busy. And so they develop shortcuts like shaking up the crucible and the diatomaceous earth in order to disperse it to increase the porosity is what they're actually doing in order to shorten their filtration time. Likewise, it is pretty common for us to talk to people about the method they're running, and let's say they're telling us they're running 991.43, and we ask them to kind of walk us through how they do it, and suddenly we hear them saying things that aren't in the method. And then when we ask them, well, wait, why do you, I can think of one example right now where they increase the temperature, I believe it's after the 3 digestion phases, they increase the temperature to 100 degrees before they go into the filtration phase. And I asked them, why are you increasing that temperature? And they said, oh, that's because it deactivates the enzyme digestion, which actually makes no sense for two reasons. One, they're at the end of the digestions anyways, and they're going to go into the precipitation phase. Two, the method does not call for that in 991.43, so there's no need for doing it. However, perhaps they were looking at the Codex method, and the Codex method does have a step where between one enzyme and another they do a deactivation by taking the temperature to 100 degrees for 20 minutes. So I'm guessing that a technician had done the Codex method and then just applied it to 99143. Again, it's not what the method calls for and can have an impact on the results, especially if some are doing that and some are not. So these undocumented modifications are made because, well, this is what someone told me to do. That can be a problem in it. So those are the kind of things we talk about when we talk about the impact. Those transfer errors, the temperature control, the mixing practices, how the mixing is supposed to be done, the issues around filtration, and just the lack of control that can happen when you have a technician. Again, I'd like to emphasize it's not because the technicians are necessarily bad, it's because the technicians are busy. And so they're not just doing this, they're called to do other things, or they have to help somebody else on another process. Everybody's being pulled in so many directions that it's going to have an impact on what they do. So when you consider the conventional method, you're talking about a method that requires a lot of steps. This is a spelled out version of the conventional method, which talks about 34 steps, but in actuality, it's considerably more than 34 steps. If you look at it, we've broken down the preparation of the glassware alone into a number of steps there. But then when we talk about scratching the filter bed as needed, this is the idea of breaking the gel. In many cases, they're coming back continuously in order to help the filtration take place. And so, it's more like 42, 43, 45 steps, depending on the samples and things like that. But if you go to the automated method, we're not using glassware. We didn't hit on this earlier in earlier webinars. We have what we call the dual chamber filter bag, which allows the digestion or precipitation to happen in one section of the filtration bag. And then filtration is mechanically separated, so when it's needed, it opens and then the filtration happens. That eliminates that transfer error. But because we're using these dual chamber filter bags, we've eliminated glassware. So we've eliminated all these steps in the preparation work. When it comes to the enzyme digestions and things like that, we've eliminated all those steps. The only thing the technician has to do is adjust the pH, because the system automatically adds the required acid in the case of 991.43, and then it's just a matter of the technician confirming is the pH within the 4.2 to 4.7 level. When it comes to the filtration process of the insoluble dietary fiber, again, that's controlled by the system and the dual chamber filter bags. So we eliminate all those steps. We manually do the acetone rinse. That allows us to do that under a vent hood, and then they have to dry the samples and weigh the samples after that. And the same is true when it comes to the filtration of the precipitation, the SDF fraction. We've eliminated all that. Again, the only thing they have to do is the manual rinse of acetone, which is also done in the conventional method. The process itself, whether it's the conventional or the automated method, you still have to do the protein correction, you still have to do the ash correction, so nothing changes. I should emphasize when we're talking about this automation that eliminates all those elements of conventional variables that can impact precision is people will say to us, well, how long does it take to do your method? And I always want to emphasize, remember, we are running the method. So we are running AOAC 99143 or 98529 or the Codex methods. And so we can't change the times. We have to do everything in accordance with the method. Where we do save time is when it comes to the filtration, because our filters have, for instance, in the insoluble dietary fiber, the IDF section, if you're capturing that, we have a surface area that's greater than 4 times more than the surface area of the Gooch crucible that is specified by the method. when it comes to the soluble dietary fiber or total dietary fiber, if you're not capturing the IDF, that filter has more than 2 times the surface area of the fritted glass crucible. And that's one of the key reasons why we can filter faster, and we eliminate the return to scratch. You don't have to manipulate the samples. Most of our samples, or maybe I should say most of your samples, are going to filter in less than 5 minutes. There have been exceptions. Psyllium husk, which cannot be filtered in the conventional method, actually has there's a modification that can be done for the conventional method using a centrifuge for psyllium husk. That will take 20 minutes for us to do a TDF. It'll take us 20 minutes to do that filtration after precipitation. But that's the extreme example. We've done a lot of samples like oat bran. It took us about 1/10 of the time it took the conventional method to do it. So our filtration times are if you will, hands-free and fast. And later, and maybe at the end, if there's questions, we can talk more specifically about the filtration. But that's one of the key benefits of us when it comes to time. Rather than a 2, 4, 6, or we've even had people tell us overnight filtration of a sample, our samples are going to be under 5 minutes, under 10 minutes, things like that. So that's kind of important to know. So we're going to look to Nick to just kind of summarize that.
Okay, thanks, Chris. So the advantages of automation and how it removes these variables. In the first case here, the transfer error is done away with. And if you're not familiar with the bag system, it's like the beaker is connected to the gooch if you were to compare it to the conventional methods, and there's a mechanical separation. So when that opens up, it's in the same container, so there's no transfer error. Everything is rinsed down into the filter automatically, so that removes that variability. Even though, like Chris said, temperature doesn't necessarily have a large effect on sample results. With our system, you'll know that every sample hit its set point. And agitation, also very important for consistency. The instrument, of course, agitates 100% during the 99143. It agitates on the 5-minute interval for the 985, and it agitates on the appropriate intervals for the 2 codex methods. So again, a lot of laboratories, if you don't use a shaker bath, they require their folks to go back every 5-10 minutes to swirl them, and that sometimes doesn't happen because they get busy. So with our instrument, there's no issue. The agitation is as per method.
And Nick, as you know, we actually had a customer that largely said, at least that's what they said to us, they purchased it largely because when they saw the agitation, they were an example of a lab that said their volume was such that they didn't have shaker bath space to do it. So I think the instruction they gave their technicians was every 10 minutes to swirl them. Again, that's not consistent with the method, but as Nick said, they just get too busy. And this director of laboratory said to us, I don't have time to watch everybody to make sure they're doing what they're told. So he says, I don't know if they're agitating every 10 minutes or 20 minutes or not at all.
Right. And okay, down to filtration here. So not only is it faster and hands-free, but the advantage of this hands-free is that no one's coming back to scratch the diatomaceous earth. So that huge area of variability is taken right out of the process. So it's hands-free and it's automated. There's no scratching, no stabbing, very consistent. And again, so automation in general is removing all of these variabilities and it's going to give you more precise and more accurate results.
Yeah, we've probably majored on improvements that automation gives that are pretty obvious, but it's just important for you to see. There is a huge difference in this. I remember being at a laboratory, I believe it was in Italy, and when we were talking about the method and I was showing that chart that talked about the glassware preparation, the director of laboratory said, oh, we don't do that. And that kind of puzzled me. I said, well, yeah, you have to do that. That's what the method calls for. You have to do the acid washes, you have to do the base, you have to do the ashing, all those things. He goes, no, we don't do that. And so when I challenged him a little bit more, and there was quite a few other labs there, everybody was kind of, surprised with that comment. And it was then that the director said, oh, well, wait a second. it is done, but it's another department that does that and brings it up to us. But the point was, they weren't considering that in their cost analysis because somebody else was doing it, and they weren't seeing the big picture. And it doesn't mean he was, not a smart person. It's just, it means everything was disconnected, and it wasn't until it was really brought to his attention that, hey, all these things are going on in order to do this method, that he made that connection and suddenly realized that he had more cost involved than he was thinking about, just because the way their organization was set up. So let's talk a little bit about results. And I need to emphasize that this is not necessarily a statistical review. We actually have, well, I'd probably say every one of the customers that have our system have done their own validation work, using good lab practices. In many cases, they've shared data with us, but they haven't given us permission to share their data, which for obvious reasons. So we've seen a lot of good data on accuracy, precision, certified check samples, and things like that. This information is based on some stuff that we have done, and where people have given us the comparisons, we have those, but we don't always get. It's interesting. Sometimes people will send us samples to test, and we ask them in the beginning. We say, okay, what method are you running? What results did you get? And if we can, we ask them to give us an idea of their precision over multiple runs of the same sample. Well, very rarely do they give us precision because they don't like to run the sample more than once. And many times they don't give us the true result because they're perhaps scared that we're just going to say, okay, here's the result we got and match the number. We like to see the data just so it's a flag for us. If we see our number different than what they report, then we ask ourselves the question, did we do something different, or are they doing something different? So we'll get sometimes results and we'll say, well, we're confident in our number, it's different than theirs. We're going to call them and tell them what the number is. And then on the phone they say, oh no, your number's good. And it kind of confuses us, and they say, well, we didn't want to give you our real number, so we gave you a number. And so, I understand that, but sometimes it's frustrating for us because we're trying to be able to compile data. So let's look first at AACC check samples. We've been involved in this program since 2012, and basically it used to be a very specific sample. In the beginning, I believe it was oat brands, and then they started, which we like, they started shaking it up and throwing in many different types of samples in it. So there are 23 or maybe 24 labs with us that have been involved most of the time. That number can change. It could be higher now. But basically, when it started, it was about 23, 24 labs with us. And so what we have in here is an indication of the results that were reported for a specific sample. So this is the number 6 sample of 2012 from AACC. And so the laboratories, the 23, 24 laboratories reports were anywhere from 14 to 19.1 for this particular sample. The red is the mean, the blue is the ANKOM result. So the results here, 14 to 19, that just shows you the variability between the labs. So intra-lab precision is not very good. And then we basically line up with the average on this sample. Same thing in the case of sample number 1 for 2013. Again, the range 11 to 16, we basically line up with the average. Now, you won't see that in every case. You'll see that there's a number of cases where we're lower, and I think, there's one where we're slightly higher. And so we do have some variation from the average on there. But again, we look to the fact that we are running the method exactly as required. We don't know what each individual lab might be doing that creates such intra-lab variation. And so we're very confident in our numbers, and where we have information about sample types and sample preparation, that might help us understand a little bit why we're high. For instance, here's 2013 number 6. We're considerably higher than the average on this one. The question is, how are these labs handling their filtration? Are they scratching deeper into the Gooch crucible and things like that? So that average is can be deceiving. You can't say the average means that's the best number, but it just gives you an idea of where all the laboratories are lined up and how we relate to those check sample programs. I think perhaps a better result to look at is this corn bran. It was corn bran samples that we received from a person considering purchasing our system, who ended up purchasing the system, but they sent us a series of corn brands that were different grind sizes and things like that. When they sent them to us, we didn't know at the time, but they also sent them to another lab running the conventional method. Matter of fact, a lab that we have a high regard for. We know that they have very good precision in their methodology. And so the person that sent us the samples shared us the results, and the lab that did those, and we were ecstatic because we lined up so nicely with these conventional methods, except for this 8013 fine bran. We were showing a higher result than they were. And the fact that we lined up so nicely with that really caused us a little bit of confusion or question in our mind, is why would we be different on this one sample? So we actually contacted the lab. We have a pretty good relationship with them, and mentioned the sample and the study. And when they went back to their records, they said, we weren't happy with that sample. Matter of fact, we don't really have a high level of confidence on the result we got in that one, but we did not run it again. So they doubted their number, and we were very confident in our number, again, because we run the method exactly as it's required, and the automation eliminates those variabilities. So, that's just showing you a specific sample type that we got. This is a series of samples that, again, we got from a specific lab that purchased our system, and they showed us what their conventional method reports were for their samples. And then there's ours next to that. Again, one that jumps out at you is the psyllium husk. Remember I said that in the psyllium husk up here, they can't filter that in their system. They have to do some, I don't know if they did the centrifuge method that is a modification that required, or what they did in it, but the bottom line is they cannot filter this through a Gooch crucible. It just will not make it through. We in a TDF can do it, as I mentioned earlier. That's one example of one that filters longer in our system. It takes about 20 minutes to filter psyllium husk after the precipitation, whereas again, you can't in the conventional method. So given our experience with psyllium husk, and knowing that psyllium husk generally has in the 80s, I don't think I've ever seen one in the 90s, but I've normally seen them in the 84, 85, 86 range for total dietary fiber. Again, we're very confident in this number because we don't know what they might have done in order to get the filtration done in theirs. So again, there is a disparity in that one, but we have a high confidence in that. But when you look at all the other results, you'll see that we basically line up quite nicely, or equivalence, if you will, between the conventional method. Why? Because we are running the conventional method. We've just automated it. The last slide I'll show you is just a snapshot. Again, this is not a statistical review, but just a snapshot of precision for both insoluble dietary fiber, IDF, and soluble dietary fiber, SDF, with a number of sample types where we ran multiple replicates. There are a couple in here, the oat flakes 1, oat flakes 2, and the oat groats. Admittedly, that's not a good range, or a good definition of standard deviation, because generally speaking, in order to do a true standard deviation, you need at least 3 results, and there's only 2 results in there. However, it still does give you an idea of precision between the 2 runs. But as you can see, even with the ones that we ran 5 or 3, or even more, I think there's one that's 6, 6 for the onions, you can see the standard deviations we were having are well below a 0.4. So standard deviation, I would be hard pressed to see a conventional lab produce the kind of standard deviation to the precision that we are producing both inter and intra lab. So that's, just kind of a big overview. Again, we're going to give you time to ask us questions and get a little bit more into the weeds as needed. But Nick, why don't you just kind of summarize for us?
Okay, Chris, thanks. So for those who maybe this is your first webinar and you're not real familiar, here is an image of the instrument, and here is how the bags are set up on here. And basically, this is what we talk about when we see the dual chamber filter bag. There's bars here that block what would be the beaker from the gooch, and they're attached basically to each other. So that's what we talked about. So this system can automate the 99143 and the 985. That is the basic model. Those two come with the base model. There is options for the two codex methods, the 2009-01 and the 2011.25. So the instrument, depending on what method you run, is able to give you insoluble dietary fiber, soluble dietary fiber. Or if you use the bags on top without the filter, you're going to get TDF all down in the bottom. So it's basically just like the method. So another advantage, of course, is that it reduces labor by up to 75%. If you saw the last webinar, I think the minimum was 50%, and I think we had as high as about 75% reduction in labor. Of course, we know labor and time is money, so reduction in labor is also going to be reduction in cost. Again, that was between 50 to 60%, I believe we came up with. And another nice thing is that this is the whole unit. I mean, this eliminates all the water baths, filtrate. This is it. This is the whole thing. There's no extra water baths. There's no filtration units. There's no glassware to prep before the run. There's nothing, every day you can just pull out new bags and get started. Nothing has to be finished. That was one thing when I used to work in the lab before I was with ANKOM. It used to make me furious. We had a method to do, and whoever did it last didn't clean up from their run, so you were an hour or 2 hours delayed cleaning up from their run. That's not an issue with our system. So cleanup and the analysis, our system is much faster and a lot more efficient. So I think that brings it to an end.
Yeah, that's it. Why don't we now take some time to take questions? Just to manage this better, there is a chat box that should be on your right hand of your screen. If you can start sending us questions on that, and then we'll just kind of go through those and ask questions or answer questions. And again, we want people to be able to leave as they need to leave. We will at some point post this on our website, so if people want to review it or share it with anybody, you'll be able to do that. So let's go ahead and stop this portion of it and go to our question and answer time.